We're going to continue on here. We've been talking chapter 14, part 2. Pretty much last time we finished up buffers. And again, remember, buffers are really the common ion effect, and it is really the only place where, as a very friendly reminder, that you should use the Henderson-Hasselbalch equation. So once again, very common errors people make is they want to use this equation in every situation. And again, it should only be used if it is a buffer situation. If it's not a buffer situation, then you definitely should not use it. Um, if it is a buffer situation, you could use it. You could also, as we've been talking about, do an ice table instead of using it. So it really is your option, but remember that is the only place where you should use it. At the very, very end, we got into titrations, and we're going to talk about titrations here today and some different types of titrations. So typically when we do a titration, we are adding for example, a solution of known concentration, sometimes referred to as a standard solution, to a solution, for example, of unknown concentration, or you could actually flip it around and stuff like that. We continue to add, for example, base to, say, acid, and we continue to do that until we reach the equivalence point. And the equivalence point in an acid-base titration means that the moles of your acid will equal basically the moles of your base. So the equivalence point is typically exactly that point where the moles of everybody equals each other. And that is usually where you want to end your titration. That's sort of like the end of the reaction. We want to get basically all our reactants used up at this point. So what we're going to look at is actually the entire sort of titration curve. We're going to talk about how to calculate the pH anywhere along your titration route. We'll also talk about some things that maybe you've seen in the past. Why, when you add, for example, 1 drop of base or something like that, you do see your indicator change a lot. That's also something else we talked about at the end there. Again, we typically do use an indicator when we're doing an acid-base titration, and that is because we're looking for some type of color change to occur as we reach the equivalence point. So very commonly, people use a lot of times phenolphthalein. There's a lot of other indicators you could use, but pretty much all indicators do work over a pH range. So phenolphthalein is like 8.3 to 10 pH. And again, at the 8.3, it is colorless, and it gradually kind of gets a pink color to dark pink color as you continue up with the pH. So ideally, when our indicator changes color, that is a signal to us that we should stop our titration. And that's usually, as we'll talk a little bit about how you want to pick an indicator, is you definitely want to pick an indicator where you can see a distinct color change. Obviously, near your equivalence point is usually where you want to deal with that. Any questions on any of that we talked about last time here? All right, then let us get into it. The first type of titration we're going to talk about is a titration of a strong acid and a strong base. And just for reference's sake here, let's just say we did hydrochloric acid plus some sodium hydroxide. So that is a strong acid and a strong base. That is going to get us our double displacement reaction, which is going to produce water and a salt in this case, which is sodium chloride. For orientation purposes here, up in the burette, in this case, is going to be the sodium hydroxide. So we're adding the sodium hydroxide to our acid, which is our HCl in this case. So we are dropping base in this case into our HCl. What we see here on the graph is what is referred to as a titration curve. And a titration curve basically gives you the pH through the entire titration. This is typically what it kind of looks like, a kind of S curve, if you will, in this type of titration. If you think about it, we are starting with here basically just acid. So we have a low pH. We're adding base. which means by the end of the titration, our pH should have gone up as we continue to add base in this case. Pretty much when you look at any titration sort of curve, there's really four important parts to the titration curve. And we're going to talk about each of these parts and sort of how you approach the pH at each of these parts. The very first part is really before you start the titration. So basically before you add any sodium hydroxide, for example, in this case, that is one part of the titration curve. The second spot of the titration curve is actually before the equivalence point. So if you're before the equivalence point, you've obviously already started your titration, and there's certain things that happen. The third point along the titration route here is really the equivalence point. And that is, as we talked about a second ago, where the moles of the acid will equal the moles of the base in this case. The fourth part of the titration curve, which if you've probably done titrations in the past, you probably didn't really get to because usually you stop at the equivalence point, is past the equivalence point. And that's the fourth sort of step. So we're going to talk about three different types of titrations, and pretty much on all these curves, these are the four sort of points that we want to look at and try to think about what's going on at each of those steps and pretty much how we can calculate the pH as we do it. So let's start with the first spot there, which is before we start the titration. So before we start the titration, pretty much sitting there in our beaker or our flask is really only HCl. That is all we got going on in there. And if we wanted to calculate the pH here before we actually start the titration, that is again a strong acid, which means if I want to calculate the pH of a strong acid, all I have to do basically is go into my pH equation at this point. And again, because this guy is going to break apart into H plus and Cl minus, you will essentially have the H plus concentration from the strong acid. And basically all you have to do is go right in there and start your, or get your pH question all about there. All right. Now let's take a look at what happens as we actually start the titration. So anywhere from the very first drop until right before the equivalence point, basically, is basically the second part of the titration curve. Now, in this case, though, we are basically adding sodium hydroxide. So we are going to get a reaction that's going to occur. It is going to be this reaction up here. And you will need to do an ice table. But now that we are adding sodium hydroxide, we're definitely changing the volume. So much like we talked about when we did buffers and we added something to the buffer, we will have to do this ice table in moles because, again, in a titration, you're doing nothing more than constantly adding volume, which means the molarity is constantly changing, but the moles are not. So we would have to do it in moles. So for step number 2 there, once we start the titration, and we're definitely before the equivalence point, we will require basically to do an ice table. So we'll do our reaction here. We'll have our HCl. We'll do our sodium hydroxide here. Again, a little sodium chloride and some water. So basically in this case, we are starting with this guy in the beaker or the flask. We are adding basically this guy here from the burette in this case. So we're going to do an ice table. And for the sake of these calculations, I am just making up these numbers out of my head. And that's where I got them from. So I'm going to say that we are starting with 4 moles of HCl. Now, if I am before the equivalence point, should the moles of my sodium hydroxide, which I am adding, should it be less than, equal to, or greater than 4 moles in this case? If I'm before the equivalence point. It should be less than, right? Because the definition of the equivalence point is they're equal. So if you're before that, what you're adding is less than, right? Till you get to the equivalence point, and then when you get past the equivalence point, what you're adding is going to be actually more than what you started with. So this is one way that you can know where you are at when you do your ice table in terms of the titration. You can get your moles of your two guys, and you can see, are they equal? Are they less what you're adding? Is it more? You'll know where you're at. So because this is before the equivalence point, I'm just again make up a number. I'm just gonna go with 2 moles here, which is obviously less. I'm gonna go 0 in this case. Now, because we are doing this and we have moles, we actually know what the change is going to be. We could clearly see that we have enough moles of HCl to handle all those moles of sodium hydroxide that are coming in. Essentially, HCl at this point is the excess reagent. And really at this point, the sodium hydroxide is the limiting reagent. So the change here is going to be actually the sodium hydroxide. You should always remember to take the smaller number because you cannot have a negative concentration. So it should always be the smaller number here. So minus 2 moles, minus 2 moles, and plus 2 moles in this case. That means at equilibrium here, we have 2 moles of this guy, 0 this guy, and basically 2 moles of this guy. So much like we talked about with buffers, and especially pretty much in most cases, as soon as you do this first ice table in moles, you really should kind of convert it back to molarity because that's most of the time what you're going to need. So you really should take these guys and convert it back to molarity. Obviously, to do so, you would use the total volume. And in this case, that would be the volume of HCl you started with plus the volume of sodium hydroxide you added, basically, right? And that will get your total volume that needs to be converted, obviously, to liters. So at this point, we want to think about what we got left. So we have NaCl, we got a little HCl. By the way, is that a buffer? That is not a buffer because remember, a buffer cannot be made up of anything strong, and that is a strong acid. This is a salt, which is a neutral salt, which means I don't really care too much about it in terms of the pH. That means really what we have at this point now is still a strong acid left over. And we just calculated the concentration of that strong acid, which will give us our H plus concentration. And at that point, you could go into your pH equation. So in this type of titration, anywhere from the first drop to before the equivalence point, you do have to do really one ice table. The purpose of that ice table is to figure out really how much of your strong acid you have left over and then get the concentration of your strong acid so then you can calculate the pH. Any questions on that there? Okay. All right, so that is the second part of the titration curve, again, before the equivalence point. Now, as we approach the equivalence point, which is coming around here at number 3, we do see very commonly what will happen when you do a titration, which is we actually see a pretty vertical jump to the equivalence point. And by the way, we usually will see a vertical jump sort of past the equivalence point. And this is what really explains what people often say when they do titrations. And I just heard it yesterday as my class was doing titrations. I just added 1 drop in my phenolphthalein, right? It went from like no color to like dark pink. And the reason for that is really what happens as you get close to the equivalence point. So again, a reminder, we take something like phenolphthalein, 8.3 to 10, again, pink heading this way, kind of colorless on this end. And when we think about what's happening as we approach the equivalence point, and really any titration for the most part, it goes vertical, which means 2 things. It means that the volume here does not change very much. You can go anywhere along that red line, pretty much go straight down. The volume is essentially the same. So we're not changing a lot of volume at this point, but we are definitely, if you look at the difference in pH, we are changing a lot in terms of the pH. The pH will change a lot. And that's why when you add 1 drop, you may find yourself at a pH like way up here. Let me change colors here. So you add that 1 drop, you had no color, and then, maybe you find yourself up here. And that pH is now closer to like 10, 11, which means dark pink for you in your titration, right? But if that really is the case, you missed it by 1 drop or 2 drops, did I really miss the volume of my equivalence point? Not really, because the volume where this green dot is and this green dot is pretty much the same volume, right? So the volume doesn't really matter. And that's why, for example, if you did that and you're really careful when you're doing your titration, maybe you had a mean instructor or not, and they made you re-titrate it if it was too dark pink, but you really didn't need to, because really the volume that you had probably was pretty much the equivalence point volume. The reason why teachers will sometimes tell you that's too dark, you need to re-titrate. The reason for that is this. Maybe you titrated like I used to do, which was just open the thing up, let it all drip in there, shut it, go cool pink. I'm going home because I'm already got my pink thing. Now, if you did that and you weren't really, really careful, you could hit that same pink way over here, right? And that would be the same pink color that you had basically over here. And now, are you close to the equivalence point? You're not. You're very, very far away, right? So if you were really careful in your titrations, you missed it by a drop or 2 drops or something like that, overall, the volume's going to pretty much be the same as what it is at the equivalence point. You don't really have to retitrate it. But if you weren't really careful, you could overshoot it pretty far. And there's really no distinction between like super dark pink and darker pink, right? It's kind of the same pink at that point when it churns. And so that's why sometimes people will tell you to retitrate it. But if you miss it by a drop or something like that, it doesn't really matter. Really, more so when you do a titration, the more important thing is really the volume to reach the equivalence point every time you do it is relatively about the same volume. And that's usually will give you a pretty good result. Any questions on that there? So that's the age-old question of why people say that I only added 1 drop and it just changed really, really big in terms of the color. So what happens though when we are here at the equivalence point? How do we get to our pH? So let's take a look at that. Do this one. So at number 3, which is the equivalence point, and we're at the equivalence point, we obviously are going to have a reaction that's going to take place. So again, we'll have our same reaction that's happening, which is our hydrochloric acid plus our sodium hydroxide. And that gives us our sodium chloride and our water in this case. So once again here, this is what we're starting with. This is what we're adding. And I'm going to make up my mole numbers. So again, I'm going to start with 4 moles of HCl, which means in this particular case, if I am at the equivalence point, how many moles of sodium hydroxide should I have? I should have 4. That's basically your definition of equivalence point. Those two guys are equal to each other. Now, this also brings up a important thing when you're doing titrations. Sometimes they may ask you what the pH is at the equivalence point, but they may not give you the actual volume to reach the equivalence point. So sometimes you do need to calculate the volume to reach the equivalence point, and there are a couple of ways that you can do that. If it is a 1-to-1 relationship between these two, you could use M1V1 equals M2V2, where maybe M1 and V1 is your acid and this is your base, and you could solve for V2 and figure out how much base you need to get there. As long as it's a 1-to-1 relationship, you could actually do the stoichiometry, which is what that's based off of, because you will know your molarity of the HCl and how much of the HCl you're starting with. You could do your mole-to-mole relationship and figure it out. The other thing that's a probably easier way as well is because you will probably know the molarity of your sodium hydroxide, and because you know the definition of equivalence point, which is it should be the same number of moles, you then would have, in terms of molarity, you would have the moles and the molarity. You could just solve for liters to using the molarity of the sodium hydroxide. So there's a few different ways that you can figure out the volume to reach the equivalence point. And sometimes in problems, they don't actually give you the volume to reach the equivalence point. So you need, the reason why you would need, for example, in a lot of cases to figure that out is at the end, say, of this first ice table, you need to convert back to molarity. So you need to know how much of the base, for example, you added to your titration to add with the acid you started with. So you'll need to kind of know that number. All right, so in this case, we do have 0 here of our sodium chloride. The good news in this case is you really can't pick the wrong number. There's only one number to choose, so I'm going to go with 4 in this case. That means at equilibrium, nothing, nothing, and 4 moles. At this point, you could, again, using the total volume, convert that back into molarity. Now, at this point, we could also, and you could also always use the ice table to figure out sort of what's going on at the end. If you're not sure, at the end, this is pretty much all we have left. This is a salt. And what type of salt is this, by the way? This is a salt that came from a strong acid and a strong base, which means it is a neutral salt, right? None of it's going through hydrolysis, so no hydrolysis here. And because of that, your pH is actually going to be 7 here at this type of titration. So in a titration of a strong acid and a strong base, you pretty much will have a pH of 7 at the equivalence point. And that's really because this is also called an acid-base neutralization reaction. What is basically happening in this case when you reach the equivalence point is you made water. If you look at the net ionic equation, coming from the strong acid, the OH coming from a strong base, you basically formed water in this case. And the pH here will be 7. So that is good in this titration here. And that's what we see here. pH is 7 there at the equivalence point. So let's talk about the fourth part of the titration curve. And I'll just use this graph since I got it here, which is after the equivalence point. So again, you decide my indicator changed color. I don't want to stop titrating. I'm having a good time. So you decide I'll just keep adding that sodium hydroxide there. As I mentioned before previously, we do typically see this secondary jump in pH after the equivalence point. And let's talk about what's happening at this point, which is definitely past the equivalence point. So to get past the equivalence point, we're still doing our reaction here. So we'll still have our reaction here of our two things. And once again, we're starting with this guy. We are adding this guy here. So initially taking my 4 moles of HCl that I'm starting with. Now that I am past the equivalence point, the moles of my sodium hydroxide, which is what I'm adding, should be less than, equal to, or more than what I started with. They should be more than what I started with. So I'm just going to go with 6 moles here, which is definitely more. Now, a switch occurs at this point because, frankly, if you just think about what you're doing, you're just dropping base at this point, really. And the HCl actually now becomes the limiting reagent as it's the smaller number. And you have plenty of sodium hydroxide because all you're doing is just keep dropping it in, right, at this point. So the change here, again, should always be the smaller number so you do not get a negative. So it's actually going to be the moles of our HCl in this particular case. That is going to get us here 0 of this, 2 moles of this, and 4 moles of this. Once again, like normal, after this ice table here in moles, we're going to use the total volume of the base and the acid together, converted to liters to convert us back into molarity. So once again, if we take a look at what we got left over, we have sodium chloride and we have sodium hydroxide. Is that a buffer? That is not a buffer either. They are actually not related to each other, right? One's hydroxide, one's chloride. This is still just a salt that's neutral, which means, again, not really concerned about it at that point. Which really means at this point in the titration, you pretty much have as the major contributor to the pH, all that hydroxide. You just keep dropping in from your burette because you miss the pink color very badly and you just keep dropping it in. So what we have here at this point is a strong base, and we now have the concentration of the strong base, which most likely would give us our hydroxide concentration. We then could calculate the pOH, do a little 14 minus, and get ourselves to the pH at that point. So past the equivalence point in a titration like this, you are really just adding strong base. And because it's a strong base, once it hits your beaker, your flask, it's going to break apart into hydroxide. And it's going to create a lot of hydroxide really, really fast. And that is why you see from the equivalence point in the graph, there is that big jump that occurs here. Because really at this point, you neutralize kind of your reactants. And now all you're doing is just dumping in really quickly a lot of hydroxide. So the pH spikes. And that's why you get that jump that basically goes to the equivalence point in this case, or past the equivalence point, basically. And you get there. Question on those 4 spots in the titration curve. All right, let's try one here. Let's do, what is the pH after you add? We'll go 23 milliliters of 0.1 molar sodium hydroxide to 25 milliliters of 0.1 molar HCl. All right, so give it a go, see what you come up with. We're doing a titration here. We'll do our reaction. We've obviously started our titration, so we'll have our same reaction we've been talking about. So our HCl, our sodium hydroxide, going to create a little sodium chloride here and some water. Once again, much like the setup of what we've been talking about, we are starting with this guy and we are adding basically this guy. So here we do need to do it in moles like we've been talking about. So to get our moles of HCl, that's going to be our volume converted to liters times our molarity of 0.1 moles per liter. That is going to get us there 0.025 times 0.1. And that's going to get us 0.0025 moles of HCl. We'll put that in our initial spot there, 0.0025 moles. We also need the moles of our sodium hydroxide, same deal. We're going to take the volume there, convert it to liters, and times it by the molarity, 0.1 moles per liter. Liters are going to cancel, and that's going to get us there. Down here, 0.0023 moles in this case. All right, any questions on that calculation there? All right, so we're going to go 0 here. Again, from really the initial line here in our table, we can figure out where we are at. Am I before, am I at the equivalence point, or am I after the equivalence point? Where am I? I am before. Again, in comparison of the moles we're starting with to the moles we're adding, what we are adding is less than what we started with. So remember, at the equivalence point, they're equal. So if my moles of what I'm adding is less than, I'm before equal, right? So I'm before the equivalence point in this part of the titration. So again, a lot of times it's good to know where you are in the titration curve because it can help you with the math part as to what math you should do. So because I'm before the equivalence point, that means whatever I'm adding really is a limiting reagent. I'm not going to have enough of it. And that is going to be the change here. Again, always the smaller number is what we're looking for. That means here we will end up with 0.0002 moles. Nothing there, and 0.0023 moles here. We do want to convert back into molarity now. So our total volume at this point is, we started with 25 mils of the acid. we added 23 milliliters of the base. So that is 48 milliliters is our total volume in this case. That is, excuse me, what we want to divide by, but obviously we do need to convert that into liters as well. So we got to convert that into liters. That's going to give us 0.048. So 0.004167, we'll call it. Could also, if you wanted to, divide this guy by the same volume. That's going to give us 0.04792 molar. Again, if you're not sure what's going on, you could kind of circle in your ice table what you have left at this point. And once again, hopefully you can recognize that that is, again, not a buffer because of the strong acid. That means we really have a salt that's neutral, so I'm not interested really in what's going on here. Much like we talked about a second ago, basically what we have left over at this point is our strong acid. And that's really the purpose of the table here for this type of titration. Because of that, that's going to pretty much equal our H plus concentration, which means our pH in this case would be minus the log of 0.004167. And that is be that number there, I think. About a 2.38 in our titration here. Questions on that one there? See how we did. 23s between those two numbers. So yeah, that falls between. Not too bad. Since that was the titration we were talking about there. Any questions on that there? So what we just talked about, again, is specific for this type of titration of a strong acid and a strong base. Things are different if you're not using a strong acid or strong base, but if you are, then this is how you figure out the pH anywhere along the curve there. Questions on that one there? All right, then let us talk about the next type of titration we're going to do. And that titration is a little bit different. And that titration is a titration of a weak acid and a strong base. So a weak acid like acetic acid, for example, plus a strong base like sodium hydroxide, again, going to do a double displacement reaction, creating sodium acetate and water. So again, kind of like the setup on the last one, up in the burette is going to be our sodium hydroxide. We are adding that to our acetic acid in this case. So once again, here we are dropping base into our acid here. All right, so just like in the last one, we do see the same four spots. So before we start our titration, before the equivalence point, at the equivalence point being our third spot, and then obviously after the equivalence point. So again, like I said, pretty much all titration curves have these four sort of parts to them in terms of what's going on. So let's talk about, like we did in the previous one, what's going on in each of these steps. So let's start with step number one there, which is before we start the titration. So at number one, this is before the titration starts. And really, before the titration starts, all you have sitting there in your beaker or flask is your weak acid. In our case here, in this example, that is our acetic acid, is pretty much the only thing that we have there. So because this is a weak acid, that means if I want the pH, I actually have to do a Ka problem. So I got to take my weak acid, I got to do a little dissociation of it into H plus and acetate. Now, again, because you have not started titration, you haven't added volume, which means you could do this in molarity. And these would be a normal sort of Ka type problem ice table, zeros, minus x's, plus x's, plus x's, and minus x, x, and x. This would go into your Ka expression, right? You would then solve for x assumption, whatever it may be, quadratic, whatever you like. When you do solve for x, once again, like normal, that is going to equal the H plus concentration. And at that point, you could then go into your pH. So as you can see, different than the previous titration where we were starting with a strong acid, all you had to do basically is go into the pH equation. Here you got a little bit more work to do here because we're starting with a weak acid versus that strong acid. But it is basically just like a Ka type problem that we did at the beginning of this chapter when we were talking about weak acids. Question on that there. All right, so we also see that perhaps in comparison to the last titration curve, our acid is maybe starting at a slightly higher pH because it's a weak acid versus a stronger acid like we had with the HCl. Again, if we kind of take a look at that HCl graph there, somewhere it is. Right there you can see it starts a little bit lower, stronger acid going to contribute more H plus to the solution to begin with. So it probably will start at a little bit lower of a pH. All right, so let's talk then about what's happening at step number 2 there, and that is before the equivalence point. So at step number 2, we are before the equivalence point. So this basically will cover anywhere from the very first drop there of your sodium hydroxide all the way up to basically your equivalence point. So clearly at this point, we are adding sodium hydroxide, which means we do have a reaction taking place. And in this case, our reaction will be our acetic acid, and we're going to use sodium hydroxide as our strong base in this case. Again, like we talked about a second ago, going to do a double displacement reaction, giving you sodium acetate and water in this case. And once again, we are starting with this guy, and we are adding our sodium hydroxide in this case. So initially, again, we do need to do this ice table in moles because we're definitely adding volume. So again, I'm just going to make up some easy numbers to kind of follow along with. So I'm going to make up 4 moles here for our acid. And again, much like we saw previously, because we are before the equivalence point, we know that the moles of the sodium hydroxide, which is what we're adding, should actually be less than what we're starting with, right? So that again is how we kind of know we're before the equivalence point. So again, I'm just going to make up an easy number like 2 sounds good. And we would have 0 in this case. So once again, similar to what we saw previously, at this point, our weak acid is actually our excess reagent, and it is actually the sodium hydroxide moles, which are actually the limiting reagent, which is the smaller number. And that means, again, the change should always be the smaller number, or really the one getting used up, which is 2 moles in this case. And we would subtract 2 moles across here. That means that at equilibrium, we end up with 2 moles of this guy, 0 of this guy, and 2 moles of this guy. Always, it is really good practice to, like I said before, just convert these things back to molarity at this point. You usually will need molarity when you continue on with the calculation. One place maybe you won't need it is maybe if you're doing something with Henderson-Hasselbalch, but still really good practice to do that. So our total volume here is going to convert this guy back into molarity. Again, if you're not sure what's going on at this point in terms of what you should do to get to the pH, don't overlook the ice table that you have staring at you, hopefully in front of you. And we can see that at equilibrium, we pretty much have this guy there, and we have this guy there. Are those 2 things related to each other? Those 2 things are related to each other. This is, again, a weak acid, and this is the salt of its conjugate base, which means that is a fancy way of saying this is a buffer, yeah? And in this type of titration, anywhere from the beginning part of the titration to before the equivalence point, you essentially will have just made a buffer. And this is what I was talking about earlier when we were talking about buffers. This is an example of you can actually make a buffer from a reaction of a strong base in this case and a weak acid. but the buffer itself is not the strong base. It is what you actually end up with at the end of that reaction. So this is like making a buffer in the solution itself. And again, the buffer here is still the acetic acid and the sodium acetate, but essentially the sodium acetate part was made by reacting the acetic acid with that strong base. So this is a way you could actually make a buffer, and you actually do when you're doing a titration. Now, because it is a buffer at this point, you do still have your two buffer options in terms of how you want to solve it. My guess would be Henderson-Hasselbalch probably would be the easiest of the two there. And you could go right into your Henderson-Hasselbalch table or formula. Or if you wanted to, you could do a second ice table. And remember that if you chose to do the second ice table, like we talked about when we did buffers, you would then want to probably set up an equilibrium with the weak acid, for example. And the important part, if you did this instead of the Henderson-Hasselbalch equation, as we talked about, is that you should have an initial value there, and you should have an initial value there, right? Otherwise, you're not doing the buffer calculation. You're just doing a weak acid. So, and again, obviously, this would be, the rest of it would be your X's. And then obviously you would solve for X and get the H plus concentration, and that would get you basically the same answer as you would get if you went into there. Any questions on that there? So definitely different than what we had in the previous titration where we had a strong acid left over. In this type of titration, what you're going to have left over at this point is a buffer. And that's why you kind of will see sometimes the pH not changing all that much, you know, in the beginning part here, because basically you're making a buffer. So it's able to resist some changes. Then we get closer to the equivalence point, and we actually do see the pH start to rise a little bit. And that is also based on what we were talking about with buffers, which is they have a certain capacity, right? And essentially in this case, what you're doing is you're continuously adding base, which is going to use up the acid part of the buffer, right? And then at some point, you're going to blow right through that buffer you made, and then you're going to see that big jump in pH to the equivalence point. So again, you kind of make a buffer, so then it's able to kind of resist pH changes for a little bit, but because you keep adding base, you're going to actually blow through your buffer, and that's going to jump your pH to the equivalence point, and that's why we see that kind of jump that occurs. Any questions on that there? Now we're at the equivalence point in this titration, so let's talk about what happens here. I think I was going the right way. Go that way. So let's say we do get to our equivalence point, and we got obviously our reaction taking place. So once again, we're starting with this guy. We are adding this guy, and we're going to do our made-up moles here. So again, I am going to start with my 4 moles of acetic acid. What I know is I've now reached the equivalence point, which means I should have 4 moles of this guy as well, right? Again, that's basically your definition of equivalence point. You should have equal moles at that point. 0. Once again, can't really mess up. Hopefully that is a -4, since that's the only number we got going on in my made up one here. Going to zero out our reactants, which is what we expect to happen when we reach the equivalence point. We're going to knock a 4 moles over here. We're going to do what we normally should do, which is, again, convert this guy back into molarity using our total volume. So at this point, what we see we have left is a salt here, if we look at what's left, and that is a salt. And whenever we have a salt, what we want to think about is, will it go through hydrolysis, right? And that's kind of important. The salt that we had in the previous titration did not go through hydrolysis. Will this salt go through hydrolysis? The answer is yes, it will, because this is sodium acetate, which basically will break apart into a sodium ion. and an acetate ion. Sodium we are not concerned about because it is group 1 and pretty much came from our strong base. But acetate here did come from this guy, which is our weak acid. And that means that acetate will actually be its conjugate base. And because it came from something weak, it will go through hydrolysis. And that means at the equivalence point in this type of titration, it is a double ice table day for you. We're going to take our salt and have another reaction happening with water. And because that is a base, it's going to accept the H plus over. And when it does so, remember, it will always make where it came from, which is acetic acid. And that's going to produce a little hydroxide action, right? By the way, without completing the calculation, I know at this point in the titration, my pH should be acidic, neutral, or basic. Should be basic, yeah. So this guy is going to be basic at the equivalence point. Again, different than the strong acid, strong base, which is basically neutral at the equivalence point because of that salt. This is going to be a regular hydrolysis ice table where you will take this guy from above, and that will then be your starting concentration here. So you're going to take that guy and pop him into here. The rest of the table is going to be zeros, minus x, plus x, plus x. Going to be there, x's and x's. This is going to go into my k what? Yeah, you need a KB here. Yes, so you do need a KB. You most likely will have only a KA, just like in like a hydrolysis type normal problem. So you'll have to use that KW to swap it from a KA to a KB. So probably a little KW equals KA, KB action to get that. At that point, you can then solve for X, and you do have to also remember in this case that X equals the hydroxide concentration, not the H plus concentration. So that's going to equal the hydroxide concentration, which is going to allow you to get to the POH and then eventually get yourself to that basic pH at that point as well. So a lot more work than the previous one where you just put pH 7 on it because all you have is a neutral salt. Here, really, you are kind of forced to do 2 ice tables. Really, the purpose of the first ice table is to figure out the concentration of your salt. And once you have the concentration of your salt, it then becomes basically like a hydrolysis type problem like we did with salts. And usually you'll have to swap out the K value for the right K value and all that. Any questions on what's going on there? All right, then let's talk about the fourth part of this titration. And as you can see here, here's the pH, 8.72, for example, here, and this titration. By the way, that is basically the titration that you did when you used phenolphthalein, which is why they chose phenolphthalein, because it goes from 8.3 to 10. And that's also why they yelled at you that you want the lightest color of pink, because the lightest color of pink would put you near the 8.3-ish, which is probably closer to your equivalence point than a darker color of pink. Now here, we're going to go past the equivalence point and see what's going on. So if we are past the equivalence point, we clearly are still titrating. We're going to take our reaction. Again, we are starting with this guy. We are adding this guy. So let's start with my same 4 moles. And if I am past the equivalence point, as we've been talking about, I definitely should have more moles of what I'm adding than what I'm starting with. So again, I'm just going to start with the 6 here, and we'll go 0. Once again, we get that switch that occurs that the acid, in this case, actually the limiting reagent, this guy's going to be like the excess reagent at this point. So the change is going to be actually the acid here. Remember, always take the smaller number, even if your head tells you not to. Take the smaller number. 0, 2 moles, and 4 moles at this point. Once again, we're going to do a little conversion back into molarity using our total volume. And at this point, we can look and see what we got going on. We have sodium hydroxide and we have sodium acetate. So we have a salt and sodium hydroxide. First off, once again, it is not a buffer, even though you have two numbers. And this is commonly where people screw up, is they get here and they go, cool, I got two numbers. I'm just going into the Henderson-Hasselbalch equation because why not? I got two numbers. Let's try it. So you should not do this. This is, again, not a buffer. So we do have two things happening at this point. Clearly, we do have our salt going through hydrolysis, like we just talked about there at the equivalence point, and the salt is acting as a base. We also have sodium hydroxide, which is a strong base. Now, between the two, which one should be probably the major contributor to the pH in this case? It is the strong base, yeah? So this guy's got to go find some water and do a little reaction, some hydrolysis reaction to produce it. Sodium hydroxide simply needs you to open the burette and drop it in, right? And that's going to produce hydroxide really quickly in that solution. So sodium hydroxide is a much stronger base. So typically at this point in the titration, we ignore the contribution of the salt because it's really not the major contributor to the pH. And we look at our sodium hydroxide, which again is a strong base. And that would mean that at this point, that would give us our OH minus concentration, which will allow us to get to the POH and then get yourself to the pH at this point. So very similar to the last one, pretty much at this point in the titration, you're basically just dropping strong base in there, and you have an excess amount of strong base in your titration, and that's going to be, again, the major sort of contributor to the pH. Question on that there. So you can see this type of titration a little bit different or kind of different than the one we previously talked about, which is strong acid, strong base titration. The good news is, you kind of have done all these problems. The key is to know when you should do these problems, right? So we basically, at the very beginning, have a Ka type of problem, a weak acid. At number 2, we should hit a buffer if you're doing everything correctly, which means you need at least one ice table in the Henderson-Hasselbalch equation. At 3, you should have a salt left over and hydrolysis happening, and that salt will always end up being basic because it will always come from a weak acid, which means it will always act as a base, and it will always accept the H plus from the water, and that will always produce hydroxide at this point. So you have to do a hydrolysis problem. That's a double ice table situation at that point. And here you need to do one ice table, and you basically will have a strong base left over, which will give you your hydroxide concentration. And as we talked about, basically just really a strong base type of problem at that point. So there's kind of 4 distinct problems: Ka problem, buffer problem, hydrolysis problem, and really like a strong base type problem. Questions on any of that there? All right, let's try one here. Let's try this one. Why not? Let's do, what is the pH after you add 21 milliliters of sodium hydroxide, 0.1 molar, to 25 milliliters of 0.1 molar acetic acid? The Ka for acetic acid, 1.8 times 10 to the minus 5. All right, give it a go, see what you come up. Okay, let's take a look. So once again, obviously we're doing a titration. We've obviously added some sodium hydroxide, so clearly the titration is happening. So we'll start with our reaction here. So acetic acid plus our sodium hydroxide, giving us our sodium acetate and our water. Obviously, we are starting with this guy and we are adding this guy. So we do need some moles here. So we'll go 0.021 liters times our 0.1 moles per liter for our sodium hydroxide here. So 0.021 times 0.1 gets us 0.0021 moles for sodium hydroxide. So we'll add that there to our table. 0.0021 moles. We'll do the same thing there for our acid here. So converting that into liters, timesing it by the molarity of our acid, 0.1 moles per liter. And I'll just put it in the table maybe there. 0.0025 moles in this case. And 0 here. So once again, we can analyze where we're at, and we are definitely before the equivalence point. Again, the moles of what we're adding is less than what we're starting with. So we are definitely before the equivalence point in this case. That means that the change here is going to be our base that we're adding. So minus 0.00210 minus 0.00210 and plus 0.00210. That is going to get us here. Looks like 0.0004 moles. That's going to be 0 and 0.0021 moles at this point. Now, we do want our total volume. So to reach this point in our titration, so obviously we started with 25 mils of our acid. We added 21 mils of our base. That's a 46 milliliters at this point. We're going to divide everybody here by the liter version of that, 0.046 liters. And that is going to get us here. Looks like 0.008696 and 0.0021, 0.0460, 0.04565, I think. Now, at this point, if we take a look at what we got going on, we have acetic acid and sodium acetate. Once again, those two are a buffer. And by the way, you should have known that based on where you were in the titration curve before you began, because you're before the equivalence point. That is always what you should hit at this type of titration of our weak acid and strong base. Because of that, we could actually go into the Henderson-Hasselbalch in this case. pH is equal to pKa plus the log of the base over the acid. pKa value there for acetic acid, 4.74. Minus the log of this guy gets you 4.74. Plus our log of our base, which is the acetate here, divided by our acid. So 0.04565 divided by 0.008696. And we got a log of it. It's plus a 4.74. Gonna give us a, I think, 5.46 pH here, hopefully. See how we did. Close there. 5.46 is right in between there. That's not bad. Since this is the actual titration there. A question on that. Now, a reminder that although it's really good practice to convert back to molarity, and you really should, you could have also went in with the moles here, right? So you could actually, if you're using the Henderson-Hasselbalch equation, you could have went in with the moles and you would get the same answer. If you're going to do an ice table instead of the Henderson-Hasselbalch, you definitely probably should use the molarity. But if you want to go in with this, the moles into the Henderson-Hasselbalch, it does work out the same, or it should work out the same, I guess is the way to say it, not there. question on that example there? All right, we would lay it up there